I'm going to start this new unit today on decision trees. And this is our first sort of encounter of a learning algorithm where you'll be implementing it from scratch and playing with data and such things. So just to kind of recap, that there are a few different issues that we need to think about when we are employing machine learning in any new task. You need to think about how to formulate your problem as a machine learning problem. Sometimes it may not be obvious. And this is essentially one of the things that is necessary, that falls into this sort of amorphous bucket called modeling the data. You have to think about how to represent your data, which is essentially feature engineering. What algorithms to use, which there's no good answer, but you'll kind of develop a taste for this as you go along. And what's the right learning protocol? And sometimes you don't get to choose. You have just given a data, you just have to use supervised learning. There's a question of representation, which touches upon this feature engineering, but also representation of your functions, so the hypothesis space. And then we have to think about the algorithms. What's a good learning algorithm? What is success? And we will encounter this notion of generalization and overfitting for the first time inside this decision tree unit. And we have to worry about how long learning will take. These are just, in some sense, this list here, think of it as a rubric that you can use for thinking about every single new learning algorithm that we'll encounter. And one way or another, we'll be forced to answer these questions for every new algorithm that we encounter. For the rest of the semester, we'll look at different hypothesis spaces and different learning algorithms. This is the concern for this unit, decision trees, and in particular, one of the more successful or sort of easy to implement algorithms out there called ID3. Then we'll spend some time on a fair amount of time on linear classifiers, looking at different kinds of algorithms which all target the same hypothesis space. Perceptron, SVM, logistic regression, they all build linear classifiers. We'll look at this idea of combining multiple of these classifiers to form this committee, which is the concern of a collection of techniques called ensembling. In particular, we'll look at boosting and bagging. And then we'll look at nonlinear classifiers, which is like saying everything else. In particular, we'll spend some time on neural networks, and I hope to wrap up this unit of supervised learning, which also might coincide with this semester, with nearest neighbors. For each of these cases, you need to think about what these hypotheses represent. What kinds of functions, or how expressive are these functions? What are the implicit assumptions, either in choosing this hypothesis space or in choosing this learning algorithm, or combining these two things? There have to be assumptions at play. And for these assumptions, what do you give up? And how do you get generalization? And of course, there's the algorithmic question. What is the learning algorithm? How do you implement it? How long will it take? What is its complexity? The usual stuff that you have to worry about any algorithm also comes into play. In addition to all these data issues, you have to think about everything that you may have seen in an algorithms class. This lecture is about decision trees, and there are three separate subunits. The first one we'll talk about is representation. What are decision trees? Some of you may have seen decision trees in other classes. Some of you have an intuitive understanding of what it is. We'll try to kind of build on that intuition. Then we look at a learning algorithm called ID3, which is actually a greedy heuristic for constructing decision trees using data. And you'll be implementing the ID3 algorithm for this homework. So at least for that reason, you might want to kind of get familiar with it. And we'll look at extensions of the ID3 algorithm, which will take us close to what is the state of the art for decision trees. So what are decision trees? You can, of course, represent your data using as a ginormous table. In this case, this table has only 6 rows, but databases is really the field of representing data with ginormous tables. And different columns represent different attributes about the data. But if I just put my data like this, there's no even semblance of how do you think about new names that are not in this list. So rather than storing the names directly, we might want to think about some features. So I just made up some features here. For every name, there's a feature. Does the name have a punctuation? Is it a yes or a no? What's the second letter of the first name? In this case, for Peter Bartlett, it is an E. Is the length of the first name greater than 5? For Leslie Cabling, say yes. And does the first name and the last name start with the same letter? Could be yes, no. For Chaim Hirsch, it's a yes. And then, of course, there's a column called label. This is if you're familiar with databases, if you're familiar with CSV file, for example, this is the kind of stuff you can store there. Now, with these 4 attributes, quick something for you to think about. How many unique rows can exist? Ignore this column. For just these 4 attributes, how many unique rows can exist? How do you come up with that number? Or maybe actually someone who's not spoken in the class. Yes. One option is 2 to the 4. How do you come up with that?
There's 4 different attributes.
Okay. What about this one here?
3 times.
Exact. Yes, that's right. 2 to the 3 times 26. So each attribute can take a certain number of values. We are assuming that everything is discrete here. There are no real numbers. Each attribute can take a certain number of values. So it is 2 times 2 times 2 times 26, which is actually 208. Now, instead of these 4 attributes or features, if you had 100, how many unique rows are possible? Someone else, maybe? Yeah. 2 to the power of 100. That's right. Yeah.
Wouldn't like the second character be punctuation?
It could. I'm just making my life easier. Yes. It could be. Yeah. But irrespective of whether the second character is a punctuation or not, the main point here is if you decide to store all possible names, this table could be endlessly long. But if you decide to featureize the data, there's going to be only a fixed number of possible rows that this data set can have, which is kind of nice until you decide to think about 100 features. Again, we're back to this problem of there's just too many. You can't represent all of the data as a table. So one of the answers that decision trees answer, one of the questions that decision trees answer is, if you want to store all the data for a data set, even after featureizing it, I can't store it in a big table because the table is going to get really big. Can I represent the data compactly? This has nothing to do with learning or anything. It's just about, can I store a data set compactly? And an answer is decision tree. It's a hierarchical data structure that represents data in this sort of a divide and conquer strategy where we'll see an example. It just so happens that this data structure can also be used as a hypothesis space. And decision tree learners essentially explore this this hypothesis space to construct a decision tree that fits a data set. So what are decision trees? For our purposes, sure, they are a hypothesis space, they are a data structure, but for our purposes, they are a family of classifiers for examples that are featureized, that are represented as a collection of features. Every node in the tree is a test for an attribute. Does this attribute, what's the value of this attribute? Or is this attribute more than some value or something like that? And every value that the test can produce becomes a branch. And then this kind of keeps going down. The leaves of the tree are the labels that we are going to that we want to predict. Let's see an example. So imagine that you're given this data set of shapes with different types of colors, and I have somehow partitioned these shapes into three groups, A, B, and C. So we're going to build a decision tree for this particular collection of examples to represent this collection of examples. But before we start, if you had to guess, what would be the label for a red triangle? Yeah. And why is that? Everything that's red is here, everything that's a triangle is also there. So it's a convenient example. Yes? Why would you say C?
Because C has one color, A has two, and B has two.
You're trying to think differently, but that's a valid argument. But the most common, the most sort of the easiest answer here is going to be B, because everything that's red is in B, and triangles are also in B. What you're doing is you're looking at a more complicated feature, essentially, like about the entire collection of examples. What are some features that you might want here? What are some features for these shapes? Yeah, color and shape. Those are both good choices. Good enough that I actually put them in the slide without actually waiting for your answer. And now we can try to build a tree. So I'm going to just work through the process, and this might seem A, rather tedious, B, rather boring, and you might be wondering why I'm not going faster, but I'm just doing this to kind of make sure that we are all on the same page. So I could ask, what's the value of color? There are three colors here. There is blue, there's red, and there's green. And when the color is red, right away, I don't need to worry about anything else. I can just say that the label is B. Right? And when the colors are blue, now I need to do a little bit more. I can ask, what's the shape? The shape could be a circle, or a triangle, or a rectangle, in which case this is a C, this is B, this is an A, and similarly for this, I have a circle or a rectangle, and I get A or B. I just built a decision tree for you. Now, how do I make a prediction using this? Well, I can now let's take that example of a red triangle again. What's the color for a red triangle? Well, what's the label for a red triangle? Well, we first check what's the color. The color is red. So from here, I check for this. I take this path down, and I arrive at a label on that. So implicitly, the person who answered red triangle, I lost track of who. Yes, essentially executed this decision tree. Now, what is nice about this is, even though there are a handful of examples here, this decision tree covers examples that don't even exist in your data. So that's like a way of going beyond what your data says. Yes.
This maybe doesn't generalize average because for the red triangle, it simply is also distribution.
Well, we are making an implicit assumption here that the red triangle belongs to the distribution of red things and triangular things. And depending on how your data shows up, it would be, imagine instead of these 10, 15 examples, there were 100,000 examples of this type. And all red things and all triangles were in B. Would you feel more confident? It becomes a numbers game at that point. Okay, so we can build a decision tree in this fashion, and you can answer questions like, what's the label for a red triangle? To answer the question, all you do is to follow a path from the root to the leaf. Every node that's not a leaf, every node that's not one of these things, is a test for a feature. What's the value of shape? Then you go down the triangle path, and then you get, essentially we are talking about, in this path, we're talking about blue triangles. Here's a question for you. What about a green triangle? What's the label for a green triangle? Uh-oh. I know, right? Really, we want something that's called a triangle here, and we need to figure out what label to put there, and that's something that hopefully when we encounter the ID3 algorithm, it will do the right thing. It will make an assumption though. Yes. The general idea for
Sure. Well, let's say that you wanted to classify here, but you don't have enough information that you can base assumption, right? So would you end up just adding more attributes to that case?
you could, there's a possibility, but it's also possible that you might add attributes that are noisy, and this is it's not the question that you asked. The question that was asked was, do we keep adding more features to partition the data so that every partition becomes pure? And if you end up doing that all the way through, you might end up fitting the noise in the data. So that's not always a good idea. There were a few other hands. Yes.
When you look at data where there's only one attribute that's just slightly different, so like for instance, with the green triangle, then look at where the red blue triangles are at, and based on those.
Yep. That's a perfectly reasonable strategy. Yes. So you might want to look at neighbors of these things. I saw your hand first. You can. In fact, here's the exercise. Start with shape, build a decision tree, and see what happens. If you do that, would you be able to predict the label for a green triangle? That's a very good exercise. Yes.
So what if you have something that responds to those attributes because you have
then it's going to fail. It's because the color feature has only 3 things here. Oh, hold on, my pen is not working. My pen is not working. Okay. So the color feature has only 3 legs coming out of it. And if you want to assign a label for a gold star, gold is not one of the tests that we are ready for, so it's going to crash. One strategy to get around it is to add an extra edge for unknown. Now, something to think about is how are we going to add any sort of a tests or labels for unknown? This goes back to prior knowledge. How do we know what's known before? There were many other hands. Yes.
You can use a feature more than once in the city. Like for example, if we take shape, add another shape once, say, well, if you're a triangle, it's going to send you the key. And if you're everything else, go down and color.
You can do that. But just as a sanity check, make sure that you don't test for a shape once you've already tested for a shape, because it makes no sense. You already know that once you're down that path, you are working with triangles. There's no point in checking for triangle again. You could use a in this example, we've used shape in 2 different places. Yeah.
Well, could you have 2 of the same thing to the same? Like you could have square and circle for this.
Oh, I see. You want square and circle to go to color, and then you'll no longer have a tree. You'll end up having what's called a decision diagram, which can be made into a tree, but it's a kind of a cooler family of representations that we won't discuss, but let's work in that space. Yeah.
So can you look at all possible paths and see which path has the most satisfying
You could. You're going to make prediction much harder. You'll have to do essentially for every example, you have to enumerate every path and look at some sort of nearness or some sort of distance between the example that you have and all the paths. And there are like I think C4.5 or C5 is a decision tree library that does not exactly that, but uses that intuition to kind of work with examples that you've never seen before. One more question, yes?
Going back to my previous question, Why did you decide to do color first and then shape?
Because I made the slide that way.
Would it change things?
Hold on to that question till we come to the topic of learning a decision tree. That is going to be the main question that we need to worry about. What is the root of the tree? If you decide the root of the tree, then you can, for all practical purposes, build the entire tree, turns out. Okay, I'm not going to pause for more questions because we have spent quite a bit of time on this. Anytime you see a new class of functions or a new hypothesis space, the question you should think about is, what is the expressiveness of this class of functions? What kinds of functions can this hypothesis space represent? And it turns out that if you kind of restrict it to what Boolean functions does the decision tree represent, it turns out every Boolean function can be represented by decision trees, plural. There are multiple decision trees that can represent any Boolean function. There are multiple structurally different Boolean trees because you can choose different variables to be a node. And another way of thinking about it is, given a certain tree like this one here, you can convert the tree into a collection of rules. So I have a rule that says if color equals blue and shape equals triangle, then label equals B, and so on. So every part becomes a different rule, and I can write a collection of rules, and turns out that if you extend this line of thinking, you can show that any Boolean function can represent show up in a decision tree. Now, here's a thought. I told you at the end of last lecture, at the beginning of today's lecture, that if your search space is every Boolean function, just give up hope, because there are so many of them. You can't find the one that is the right one. Then right after that, I launch into this topic of decision trees, where I tell you that every Boolean function is a decision tree. So the act of learning a decision tree is no different from the act of searching over the entire space of Boolean functions, right? Because it contains every Boolean function. It turns out that's true, which means that we cannot possibly explore the space of all Boolean, all decision trees that represent your data, and we have to make approximations elsewhere. In this case, we'll make an approximation in our learning algorithm. Rather than we'll leave our hypothesis space to be all decision trees, and then we'll change our learning algorithm and say, you know, the learning algorithm is kind of broken. It's not going to explore the entire search space. It's this greedy heuristic. In a decision tree, the outputs, the leaves of a decision tree, in the example that we have seen, the leaves are categories A, B, or C. There is an entire family of work on something called regression trees, where the outputs are not categories, but actual functions. So regression trees are extremely successful for a whole bunch of applications, but we won't cover that in this class. And if you're interested in that after we finish this unit, I can send you some references. You can reach out to me. The nice thing about decision trees is that they are very, very simple in the sense of conceptually, you've invented a decision tree at some point in your life. I guarantee. You've taken some data and kind of partitioned it. Oh, I need to put, if this happens, then I do this, then I check for some other condition. You've invented a decision tree, everyone's done it. So there's a nice intuitive understanding for what they are. And they've been around for long enough that there are really well-studied methods for handling things like noise, handling missing features like the green triangle, for example, and such things. So it's really well explored, the space of the conceptual space around decision trees. We've only considered features that are discrete. We have triangles and squares and circles. What if instead of a feature that's discrete, we have a real number? We have something like, say, the length of something or the weight of a car. How do we handle discrete features? Any ideas? Yes. Well, you've spoken a lot today, so someone else. Who was? Sorry, who was talking? Okay, yeah, I've not heard your voice. So yes. So the one proposal is you have a real number, let's call this the real line. You will break it down into ranges. Maybe this is one and this is one and something like that. Any other ideas? Someone was talking here, but I couldn't tell who. Someone else. Maybe anyone else? Any other ideas? Yes.
Like, decimals, like, something, like,
You can cut it into, so if you have a number of, you decide everything that comes after this is uninteresting, which means you have exactly 1000 possible values and you take to the nearest. Turns out that's actually very, very similar, but not too far off from this idea, because 1.872 and 873 are going to fall into the same bucket and you have 1000 buckets. Yes. You could do that, and that's going to get a little bit more complicated. Yes, you could. Essentially, the proposal was you can assign weights to edges, and there are algorithms which do that. In the simplest case, for example, if your homework problems decide to take that form, you wouldn't have to do that. The simplest strategy is essentially discretize them. Do not, if you have length, and in your training data, you see 100 different lengths, do not put all of them as, different branches going out, because it's entirely possible you will see a length that was never seen in the training data. Instead of that, you discretize your features. So for instance, if you have these two features here, x and y, both real numbers, I can choose to partition the data into these sort of buckets. I break down the x feature into these ranges. Anything less than 1 to 3, and anything more than 3. But even better than that, I can actually consider each branch here as a separate text. Is x less than 3? Yes or no? If it's yes, then you're on this side. Did I say less? Yeah. If it's yes, then you're on this side. If it's no, you're on this side. And so on. And similarly for y. Once you do that, and you can build trees, because we're back to this idea of, you have discrete decisions. Interestingly, if you do that, it turns out we can examine what is something called the decision boundary. What is the boundary between labels, where when you cross the boundary, the label changes. So from minus to plus, or from plus to minus. By discretizing these numeric features into these ranges, or into these binary tests, you can construct complicated nonlinear decision boundaries using decision trees. You can construct rather complicated nonlinear functions using decision trees. So that makes them quite interesting. Now, it may not seem like much to you. At this point, we've not encountered this linear versus nonlinear distinction. So it may not seem like much to you. But for the large part of modern machine learning, the focus was primarily on linear classifiers and linear regressors. Why? Because we know algorithms that work well with them. It's only recently that we've kind of given up this idea that life is linearly separable. But decision trees could do that from, well, this must have been from the 70s or something like that. Quick summary of what decision trees are. They are essentially data structures that can represent any Boolean function or any discrete function. And it's a natural way to represent a lot of data. So if nothing, you can think of it as a compact compact way to just store data. The way I kind of internalize decision tree is to think of 20 questions. Every question in the 20 questions, the game of 20 questions, every feature is one of those questions, and you wind down some path and you get to the answer. Which means prediction is easy. You just go down the tree and you're done. I'll leave this question as I'll say this thing and leave it as an exercise. Given any data set, even the small data set that we had with the triangles and the colors, given any data set, there are many structurally different decision trees that can represent it. We've kind of touched upon the answer to that already, but I'll leave it as an exercise for you to think about for later. Any questions about decision trees? Yes.
What about the green triangle?
What about the green triangle?
How do we communicate that to classify it?
Given that data, we have to make an assumption. You want to decide whether the green triangle is more green or more triangle. If it's triangle, it becomes a V. If it's green, then it kind of targets the boundary. So this is where there is no learning without assumptions. In your worldview, are green triangles more green or are they more triangles? And based on that, you and I might come up with different models, even with that tiny data set. So anytime you anytime you employ a learning algorithm, you have made an assumption. You have made an assumption about what features to use, which features are important, what algorithm to use, what hypothesis. And all these choices decide what label that green triangle will get. Yes.
Is there any importance to areas of the tree? If I can say that this is there any or is it just including functions and you don't care?
Oh, I see. So the question was, suppose I give you a decision tree and you take two nodes in the tree, you can ask how far are these nodes from each other by walking along the tree. And the question is, does this mean anything? What it actually means, that's an interesting thought. I've not thought about it before. What it means is it's you can think of it as a measure of similarity between examples that fall under this subtree versus examples that fall under that subtree. So it's like a similarity measure that is decision tree dependent, which is kind of cool. Yeah. All right. Our next concern is now that all of you are experts on what decision trees are, the next thing is to figure out how to build them from data. And that's going to be the thing that's going to keep us busy for the next 15 minutes and a good part of the next lecture. So we've already seen what decision trees are, and let's now worry about the learning algorithm. I kind of mentioned this earlier. Research on decision trees has been around forever. There's work in psychology in the 1960s which talks about this. Perhaps in the context of modern machine learning, the name that always comes up when we talk about decision trees is Ross Quinlan, who developed this algorithm called ID3, which has a name that I can never remember, iterative dichotomizer 3. I guess it's the third of the lot. It's an algorithm. It was Quinlan invented this in the 1970s. The main contribution of this algorithm is this heuristics that we will look into in some depth, called the information gain heuristic. And that's the key, sort of the heart of this algorithm. After that, there was sort of pioneering work by Leo Breiman, Friedman, and their colleagues, essentially people from statistics, who developed a family of algorithms called CART, classification and regression trees. There's a book with that name if you're interested. Since this area has seen a lot of work, this was a very rich area of exploration in the 1980s, 70s, and 80s on dealing with noise, on dealing with features that are not real valued or that are not discrete. I mean, dealing with examples where certain features are just missing. Remember, features are like sensor reading, and maybe your sensor broke down that one day, and so you couldn't get a particular value of a feature. Does this mean you can't classify that example? No, you can. In the context of decision trees, these sort of simple ideas for dealing with missing features were invented. I think after that, Quinlan had updated algorithms, C4.5, C5.0, and they are more commonly used. I think the libraries that implement machine learning algorithms today have these baked in, C4.5 and such things. Just last week, for the first time, my students and I came across this book called C4.5, written by Quinlan. I didn't know it was a book, and it's fantastic. I showed these guys also. It has the C source code for that algorithm printed in the second half of the book. If you want, I mean, the book comes with the source code, and if you want an implementation, you just have to type up about 100 pages of C. Pages of C. It's a unit of measurement of programs that I've not seen before. Anyway, hold on, I'll get you in a minute. Something interesting that happened in the around 2000s, early 2000s, is some work by Rich Caruana and colleagues who showed that when a single decision tree might not be a fantastic learning system because it may not generalize well. But when you build many small decision trees and build a committee out of them and ask them all to vote on the answer, essentially like the wisdom of crowds, it ends up becoming a really good general purpose machine learning system. And for a little while, these boosted or bagged decision trees, as the ensembles are called, were considered the very best thing you could do if you want to deploy machine learning. If you want to write papers about machine learning, you can do things about linear classifiers and such things. If you want to deploy machine learning, invent new features and build decision trees. This was the conventional wisdom till maybe about 2012, 2013, until neural network libraries became more robust. But even now, decision trees are really, really useful because whenever we talk about building models that are interpretable, that are human understandable, that where you see the model, the classifier, and you can actually you have a sort of an audit trail of why the decision was labeled B. You might want to think about decision trees because decision trees are easy to interpret. Unlike pretty much every other learning algorithm and every other hypothesis space that we will encounter. There was a question at the back. That's a shame. That's just so sad. Yeah. Okay. I don't know what to do with that knowledge. Anyway, let's look at an example today. We have 10 minutes. Let's look at an example of building a decision tree, and we'll continue on Thursday with this information gain heuristic. For today, the example, this is from a paper from actually Quinlan's paper on playing tennis. If you're interested, this paper is linked to on the class page for the decision tree unit. After we finish the lecture, after we finish this unit, I encourage you to try to read the paper. You'll find that it's easy to read because we are essentially basically covering that paper. So imagine that we need to decide whether we have to play tennis today. And rather than going outside and deciding to play tennis or not, we can kind of try to avoid playing the game as much as possible by building a decision tree. And the way we do that is we try to get all these features. Outlook, it could be sunny, it could be overcast, or it could be rainy. The temperature could be hot or mild or cold. It could be high. The humidity could be high or normal or low. And it could be very windy or it could be not. So there are 4 features all about the weather, and they have these values. They can take these values. And the task here is a binary classification task. Should I play tennis? So the label is plus. Or the label is minus to say that I'm not playing tennis. And in order to build this decision tree, let's say that I've collected data from the previous 2 weeks of my playing tennis. So there are 14 rows here, and every row here represents a certain instance of whether or not I play tennis based on the weather. So the one that I circled says the outlook, this is outlook. The outlook was rainy, the temperature was cool, the humidity was normal, and the wind was weak, and I decided to play tennis on that day. This is just a data set from the Quinlan's paper. Now, the basic algorithm for constructing a decision tree is it's a batch algorithm, which means it assumes that all the data is available at this point, and I'm going to do some repeated processing over this entire collection of data again and again. And just to kind of give away the punchline, it turns out that there is a decision tree. Of course, there's a decision tree that represents this data, right? We can, just like we did with the triangles, you can pick a feature, partition, pick a feature again, keep partitioning, and we could have done that. And if you started with Outlook and made all the same choices that I did, you would end up with this decision tree. So the goal of the decision tree learner is to recursively build a tree from the top down. First, pick a feature, and then go down these paths, and then decide what to do next. There are really only two decisions, two sort of things that this decision tree learning algorithm needs to do. If you think about it, the first one is it needs to decide which attribute is the most important one. Should I look at this attribute called outlook or humidity or wind or temperature? Whatever algorithm decided to build this particular tree decided that the outlook feature is the most important one. Okay, then we know from our understanding of the data, remember that we have all possible values that these features can take. From our understanding of the data, we knew that outlook could take only 3 values. It could be sunny, it could be overcast, or it could be rainy, which means the next thing that the learner needs to do is for each of these values that the feature can take, it needs to decide what to do next. To give away the punchline, what to do next is essentially to build the rest of the tree, right? Building the rest of the tree is the same as building the tree. So we can make a recursive call to whatever algorithm built the tree for us in the first place. This is essentially the idea of the ID3 algorithm. We'll go into it in a little bit more detail. In fact, I'm going to go over the ID3 algorithm now. Essentially, walk through the algorithm, and then we'll pick up from the algorithm again on Thursday. So the algorithm looks like this. Right now, it's an empty screen, but the ID3 algorithm takes a data set called S as its input and a collection of features or attributes that are currently relevant for this data set. Now, let's consider the easy case first. You're given a collection of examples S, and suppose every single example in that set had the same label. Let's say it was all plus or all minus. Well, we don't need to look at the features, right? We just say the label's plus. If you were so lucky that your data set had all the same label, why are you even bothering implementing a learning algorithm? Just say whatever is that label. So that's the easy case. If all the examples have the same label, you return a node, which is a leaf, with that label. We are done. Life is never that easy, or not always that easy. We have to deal with otherwise. If all examples don't have the same label, then we create this root node. And we need to now decide which feature goes into that root node. In the example that we saw, is it going to be outlook? Is it temperature? Is it humidity? Or whatever was the fourth one? Wind. We need to decide which of those four features goes into that. So we're going to create this empty root node and then populate it with a feature. And then eventually we will be sending out this root node to whoever calls this algorithm. The next thing to do is we need to use some heuristic, and this is a part that I will come to later. Suppose we have some method that decides among all the attributes that are currently relevant, which is the best one to put inside the root. So I have an empty root node. Maybe I need to decide whether it's outlook. Here. And I have a heuristic that tells me which feature is the best one to place in the root of the tree. Let's call that feature A. A is one of these features that we have. This feature can take multiple values. Outlook took 3 values. This feature can take possibly many discrete values. And for every possible discrete value of that particular feature could take, we need to create a separate branch. So suppose we've decided that outlook is the root of the tree, and there are 3 features. We're going to add 3 branches here. I don't remember what values outlook took, but I know there were 3 of them. And we've created a new branch And now inside this new branch, let me actually look up what value outlook. Is it sunny? Yeah, let's say sunny. So suppose we are inside this branch here called sunny. Now we can look at the subset of the examples. So we have a collection of examples here, right? We can look at the subset of examples where the outlook is sunny. That's going to be essentially we are partitioning the data into three groups here. The subset where the outlook is sunny, the subset where the outlook is whatever value goes here and whatever value goes here. And let's say that that subset for outlook, that feature is S sub V. S sub V is a set of examples where the attribute A has a certain feature, certain value V. Now, suppose that S sub V is empty. Possible, right? Maybe it's like the green triangle. Suppose we don't have a single example where in the set S, where the feature takes the value that one of those values. Any ideas on what we can do there? Can you speak up? You could delete that branch, but then when it's going to give us grief when we encounter examples of that type later. Yes, that's right. You can invent a default label. Now, a good value for a default label is the most common value, the most common label that you have in your original set S. I'll leave it as an exercise for you to think about why this is a good choice. Let's now, in the minute that we don't have, quickly talk about what to do next. If it turns out that this set is not empty, then we have a set of examples and we need to build a tree. We have an algorithm that can take a set of examples and build a tree. Just call this algorithm again, but using only the subset. We are out of time, so maybe can you, is this a short question or?
Yeah, it is. What, I mean, this is kind of a problem with your space though. You want to go back and
Let's actually begin with that. Can you ask that question again? Okay, awesome. Let's pick up from here on Thursday. Watch out for homework where you'll be building decision trees, both in code and on paper. And I'll see you all on Thursday. Thanks.